One of the most famous problems in quantum mechanics that uses constant potentials is the particle in a box. So let's take a look at this problem and see why this is such a popular problem. The particle in a box problem is a problem where we're going to confine a particle to be in a certain region in space. So we're going to take and make ourselves infinite potential walls, and we're going to put our particle in this region in space where we have it between 0 and L on the x-axis. So we can do this in 3 dimensions or 2 dimensions, but right now let's just do it in 1 dimension and see what happens. We're going to make the potential equal to 0 inside the box. And we know what the solutions are inside the box. And we've said that when we have a bound particle, so if our particle is outside here, that there is some finite probability of being in this classically forbidden region. However, if my potential goes all the way up to infinity, then it turns out that the particle can never be outside the box. And so what I've done by making the potential equal to infinity is to confine the particle to be in this region in space. So let's see what happens when we confine a particle to a region in space. So we can immediately write that the wave function out here outside the box is equal to 0. There's no particle out there, so there can't be any wave function. So outside the box, the wave function is equal to 0. And inside the box, we have a 0 potential, so our energy is always greater than our potential. And so we're going to write the wave function as c1 e to the ikx plus c2 e to the minus ikx. So we have these traveling waves. The particle can be going in the plus x or the minus x direction, and it can travel back and forth in this box. Okay, so that's what our wave function looks like. Now, the issue is that this wave function needs to be continuous across the entire range of x, including outside the box. So we have to have a continuous function. And that means that psi at 0 for outside the box has to equal psi at 0 for inside the box, because I have two different expressions for the wave function outside and inside. And in addition, the psi outside the box at L, at my other boundary, has to be equal to psi inside the box at L. And so these are what are called boundary conditions that ensure that my wave function is going to be continuous. And I need to apply these. I need to make sure that these work. Okay. So before I get started actually doing this, we're gonna manipulate this equation a little bit to help us do this in a little bit easier way. So a math trick that you need to learn that is important for you to understand is that e to the I theta is equal to cosine theta plus I sine theta. And e to the minus I theta is equal to cosine theta minus I sine theta. And we're going to use this little trick, these relationships, to go back and forth from imaginary exponentials to sines and cosines. It's a little bit easier to think about what a sine and a cosine looks like than it is to think about what an imaginary exponential looks like. So we can write psi x inside the box as c1 times cosine, now our theta is k times x, plus I sine k times x. And then we have c2 cosine kx minus I sine kx. And so if we collect our cosine terms, we have C1 plus C2 cosine kx. And if we collect our sine terms, we have C1 minus C2 times I sine kx. So this and this are just constants. And so I can rewrite this as A cosine kx plus B sine kx. So there's my wave function inside the box. And now what I need to do is I need to make sure that these boundary conditions are met. So let's start with the one at 0 and write what we know. So outside the box at 0, or anywhere outside the box, the wave function is equal to 0. And so 0 has to equal this function inside the box when x is 0. So if I put in 0 for x, I have a times cosine of 0, that's a, plus b times sine of 0, but sine of 0 is equal to 0. And so this tells me that a has to equal 0. And so if a equals 0, then my wave function inside the box is just b sine of kx. So now let's make sure that our wave function matches at x equals L. So in this case, we have to make sure that the wave function outside the box at L, so 0, is equal to the wave function inside the box when x is equal to L. So we have b sine k times L is equal to 0. And sine will only be 0 when its argument, so kl, is equal to an integer number of pi. So think about what the sine function looks like. So sine of x looks like this: 0, pi, 2 pi, 3 pi, and so forth. So every integer value of pi, sine crosses 0. So we know that KL is equal to n pi. So that means that our k values have to be n pi over L, where n is equal to 1, 2, 3, so forth and so on. So this is our first example of a quantized system. So notice that because we have to have a continuous function, that restricts our values of k to integer values of pi over L. And so our wave function inside the box then is equal to b sine n pi over L times x. And our wave functions, we have a set of wave functions, one for n equals 1, one for n equals 2, one for n equals 3, and so forth and so on. So we have a set of wave functions that are quantized according to the integers 1, 2, 3, or the quantum number n. So one way to think about this is that because our wave function has to be 0 at 0 and L, that means that only half integer wavelengths are going to fit inside this box. So I could put this much of the sine function inside the box because the boundaries would be at 0, or I could put this much of the sine function inside the box because the boundaries would be 0, or I could put this much of the function inside the box because the boundaries would be 0. So I have to have these half integral wavelengths of the particle, and k, remember, is related to the wavelength of that particle. And so only integer values of pi, or half integer values of wavelength, will fit inside the box. And that has to do with the fact that we have to have the wave function be continuous at the boundaries. So now that we've sort of figured out what that wave function is, we're not done until we actually figure out what our energies are. So remember that we have a zero potential energy inside the box, and so our particle has only kinetic energy. And so its energy is p squared over 2m, and p squared is h bar squared k squared over 2m. But k, we just said, was n pi over l. So we've got h bar squared n squared pi squared over 2m l squared. And those are our energies, and they depend on the quantum number n. Now, remember that h bar is equal to h over 2 pi. So I can simplify this a little bit by plugging in h over 2 pi squared for h bar squared. And then I have my n squared and my pi squared over 2m l squared. So I have a 1 over pi squared from my h bar squared, and so I should be able to divide out those pi squareds. And then I have a 1 over 2 squared in the numerator, which brings a 4, 2 squared is 4, so it brings a 4 down to the denominator. And so I can rewrite this as n squared h squared over 8m l squared. So finally, my quantized energies that are quantized according to the quantum number n are equal to n squared h squared over 8m l squared. So the wave function and the energies are quantized for this system where I have confined the particle to be in a region in space. And it's that confinement of the particle that leads to the quantization.